Alright, this video was created for my Chemistry 140 class called the Introductory General College Chemistry, and the purpose of this video is to address a few problems that we had on our first quiz that dealt with calculations and significant figures. So the first question was, what is the temperature in degrees Celsius if the temperature in degrees Fahrenheit is negative 4.6 degrees Fahrenheit? All right. So when we look at a problem like this, first of all, we got to look at this measurement, and we need to think about how many significant figures in this number. Well, there's two significant figures. And where does the least significant figure lie? Well, it lies in the tenths place. So the tenths place is our least precise part of the measurement. Next, what we need is we need to look at the differences between the degrees Celsius scale and the degrees Fahrenheit scale. If we look at degrees Celsius, water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. And if we look at the Fahrenheit scale, water boils at 212 degrees Fahrenheit and it freezes at 32 degrees Fahrenheit. So the number of units between freezing and boiling on the Celsius scale is 100 units difference between freezing and boiling. On the Fahrenheit scale, it's 180 units. So if we're trying to convert degrees Celsius into Fahrenheit, it would be degrees Celsius equals 5/9 times degrees Fahrenheit minus 32. All right. Now you say, what's the 32? Well, the 32 is the offset between these two scales when we're talking about freezing. 0 degrees Celsius is 32 degrees Fahrenheit. So we have to offset that. That's a counted number. It's an exact number between the Fahrenheit scale and the degrees Celsius scale for the freezing point of water. Now, our book simplifies this. They actually say degrees Fahrenheit minus 32 divided by 1.8. So what's happening here is we're taking the 5/9 and we're moving the 5 down into the denominator of the denominator, so it's 9/5, and we get this 1.8. So again, yeah, just a side note, what we're doing is we're saying degrees Celsius equals degrees Fahrenheit minus 32, and then the 9's in the denominator, we're putting the 5 down in the denominator like so, and that's legal. That is, these two things are equivalent. All right, and 9 divided by 5 is 1.8. So this is the more common way we see the equation today. Actually, when I went to school, this was probably the most common way. All right, both calculator, yeah, we like this method. So again, what I want to point out here, this is an exact number and this is an exact number. All right. So when we go to calculate our answer, we're going to take the measured value, negative 4.6, and we're going to subtract 32 from it. All right, let's do that first. And when we do that, we're going to get for an answer negative 27.4. That's not correct. Let's try that again. 4.6 minus 32, negative 36. There we go. I forgot the negative sign. Didn't quite work out for you there. All right, negative 36.6. Now, how many significant figures should be in this number? Well, remember on addition and subtraction, it's about the place. It's not how many significant figures you have. It's about what was my least precise part of the measurement. Well, this is an exact number, so this does not affect the significant figures whatsoever. This number was measured to the tenths place. So we do know this number over here to the tenths place. So oddly here, we actually gained a significant figure. But again, that's not what we're talking about as number of significant figures. We just want to know the place. So now we have negative 36.6. We're going to divide that by this exact number, 1.8. And so when we do that, we get negative 20.3333, and that would be in degrees Celsius. But not all of these threes are significant. How do we determine how many significant figures should be in our final answer? Well, this number has 3 significant figures, and this number is infinite. It's an exact number. So we should have 3 significant figures in our final answer, and that would be negative 20.3 degrees Celsius. All right? So again, this determines, but because we did this subtraction here, we actually gained a significant figure. This was an exact number, does not determine number of significant figures, so we end up with 3 in our final answer. All right, next problem. The next problem was give the answer to 5.0 times 10 to the negative 4, and we're going to subtract from that 6.0 times 10 to the negative 5th. Oops, it's 6. It's not 6.0. 6. Let me redo that. 6 times 10 to the negative 5th. All right. So let's do a check here. How many significant figures in 5.0 times 10 to the negative 4? 2 significant figures. How many significant figures in 6 times 10 to the negative 5th? 1 significant figure. Now, the tricky thing about when you're adding or subtracting exponential notation numbers, you need to get the powers of 10 to agree with one another. So what we're going to do here is let's think about this. Which number is larger, 5.0 times 10 to the negative 4th or 6 times 10 to the negative 5th? All right, if you said 5.0 times 10 to the negative 4th, you are correct. So what we would do here is I would say this is 5.0 times 10 to the negative 4th. Now, I'm going to change this smaller number into a number that also has 10 to the negative 4th for the exponent. All right, so how do we do that? Well, if I make this 0.6, that would make this times 10 to the negative 4th. All right? So when we subtract these two numbers, we can do that now because the exponents agree with one another. We get 4.4 times 10 to the negative 4th. All right? Now some of you may be saying, well, what if we did this? What if we said 5.0 times 10 to the negative 4th and we converted that to 50 with the decimal here times 10 to the negative 5th? Yeah, you could do that. I don't know why you do it, but let's look at it and see what would happen. This becomes and this was 6. Yeah, let's leave the decimal off, but 6 times 10 to the negative 5th. So what we've done here is kept the exponent of the 6 in its original notation, and we've converted the 5.0 times 10 to the negative 4th to 50 times 10 to the negative 5th. Now when we do this, we would get 44 times 10 to the negative 5th. Now, when we go to put this in scientific notation, it always has to be a digit, the decimal, and then the rest of your significant figures. So we had to move, to make this a digit, the decimal, and the rest of your significant figures, we had to move the decimal over from 44 to make it 4.4, and that's going to make this exponent to the negative fourth. So this is the correct answer. What's your exponents? All right, next question. The next question, a little bit more complicated. All right. So they tell you that the area of a rectangle, is length times width. Length times width. If the rectangle has a length of 32.6 centimeters, and has a width of 72.6 centimeters, what is the area of the rectangle to the correct number of significant figures? All right. So all we need to do here is, first of all, let's count how many significant figures we have. These are 3 non-zero digits, so that's 3 significant figures here. And this is 3 significant figures in 72.6. And so we're going to multiply these two numbers together. And that equals 32.6 times 72.6 equals 2,366.76. And what's the units? Centimeters squared. All right? Centimeters squared, because you multiplied centimeters times centimeters. Now, that's my rough answer. What is my final answer? How many significant figures should I have in my final answer? Okay, with multiplication and division, you look at the numbers that you are multiplying or dividing, and whichever number has the least number of significant figures, that's how many significant figures should be in your final answer. So both of our numbers have 3 significant figures, so our final answer should only have 3. So we go 1, 2, 3. We look at the number adjacent to our least significant figure. If this number is 5 or greater, we round this number up. So my final answer would be 2,370 square centimeters. Now, there's some ambiguity here. Is this 0 significant or not? Now, I'm not saying that it's not important. It's a 0. It is acting as a placeholder to keep the 7 in the tens place, the 3 in the hundreds place, and the 2 in the thousands place. But is it significant? Well, it's not. We already said that this number should have 3 significant figures. Here they are, 1, 2, 3. But there is some ambiguity here. Some people would maybe think it's 4. Some people would say it's 3. So the two ways to fix this is to either write this as 2,370, and if I wanted to convey 4, I'd put a decimal like that. You could do it that way. But because we're only conveying 3, and you have this 0 here, a lot of times the best thing to do here is to write this in scientific notation. 2.37 times 10 to what power? Times 10 to the third. Convey, because in scientific notation, only those digits that are significant are in scientific notation. So this would be the best answer. This answer has some ambiguity to it. But I would accept either one. In my class, if you want to convey that this has 4 significant figures, you should put a decimal right there. If you don't put the decimal there, I assume you're talking only 3 significant figures. All right. Last question, another temperature conversion problem. In this problem, they tell us that the temperature is body temperature, 98.6 degrees Fahrenheit, and they would like to know what that temperature is in Kelvin. All right. So I don't know the relationship between Fahrenheit, degrees Fahrenheit in Kelvin, but here's my plan of action. I'm going to take the degrees Fahrenheit, I'm going to convert that to degrees Celsius, and then I'm going to convert that to Kelvin, because I know that the relationship between Fahrenheit and Celsius and Kelvin. So what are the relationships? Well, again, we just did the Fahrenheit one. Degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. And the Kelvin, notice there's no degrees in Kelvin, it's just Kelvin, equals degrees Celsius plus 273.15. All right. So let's get started. We're going to take, to find the degrees Celsius, we're going to, actually, let's do it this way. Let's just do it this way to show you could do this. Kelvin equals 98.6 minus 32 divided by 1.8. And then after we get that answer, we're going to add 273.15. All right. All I did here was called substitution. I substituted in the formula for the formula to convert degrees Fahrenheit into Celsius into our Kelvin equation here. All right. So let's look at significant figures. Infinite number, these are exact. So we're going to take 98.6 divided by 32, or subtract it. 98.6 minus 32, that's 66.6. All right, so this is 66.6, and that is the correct number of digits. This place is known to the tens place. This number should be known to the tens place because we're doing subtraction, and this 32 does not determine the number of significant figures. So 66.6, we're going to divide that by 1.8, and we get 37. All right. Now, this 37 is actually known to 37.0. Even though your calculator says 37, because this has three significant figures, and we're dividing by an exact number that has three significant, an exact number that has infinite number of significant figures in 1.8, we should preserve that and say that this has three significant figures. All right, so we're going to add to that 273.15. All right, so let's do that. Add to the 273.15. All right, so this number is known to the hundreds, this number is known to the tenths. So we can, when we add these two numbers together, we get 310.15. 310.15. Since both numbers are known to the tens place, we can report our final answer to the tens place. And since this number, so we look at the 1, we look at the number adjacent to it, which is 5. 5 or greater, we round up. My final answer for this one would be 310.2 Kelvin. 310.2 Kelvin. Again, measured quantity based off of this measurement. 32 is exact, 1.8 is exact. This is a measured quantity as well. That's why it's got the digits after it. That shows the relationship between degrees Celsius and Kelvin temperatures. So both of this number is known to the tenths and this one's known to the hundreds. We're adding here, so we can only report our final answer to the tenths place. So 310.2 Kelvin. Well, I hope this clears up the errors that you've had in dealing with calculations in significant figures. What I would suggest is to go back to section 1.3 in the first chapter, which starts on page 11, and read over that a couple of times and do some problems, because significant figures are very important to a scientist. They convey how precise the measurement was made. The more significant figures you have, we assume the more the precise the measurement is. And generally that precision gives us some expectation for accuracy, although the two are separate. Accuracy is how close to the actual value you are, or the true value. A lot of times maybe you're making the measurement inconsistently incorrect. Maybe your ruler's tore up. Maybe somebody sawed off a centimeter. And then everything you're measuring very precisely, but because the ruler is broken, because it's lost a centimeter, it's measuring everything incorrectly. But if there is no operator error, generally precision, how reproducible the results are, denotes accuracy. I hope this helps, and if you need more help, please contact me. Thanks.